My pleasure to introduce Yike Wang from the University of Washington. She's a student of Yulia and Hannah's, and a bunch of us noticed her ScienceMeter paper, which investigated really interesting questions about sort of how language models could internalize scientific knowledge from papers and also project some future scientific knowledge. So she's going to talk to us about that work today.
All right. Thank you so much for the introduction. Can everyone hear me? That's good. All right. All right. Thank you so much for inviting me to give this talk today. And I'm so flattered as like the first bunch of people enjoyed this super good conference room. So today I will talk about our recent work, ScienceMeter, tracking scientific knowledge updates in language model. And it is a joint work with Shambin, Yulia, and Hannah. All right, let's get started. So these days, large language models have been widely used to add scientific research, revolution the way that research approach complex questions and innovate in their respective fields. So studies have shown that a language model can help with various stages of research cycle, including literature review, hypothesis generating, idea development, experiment, and even experiment planning and implementations. It shows significant potentials in driving scientific advancement across various domains, including computer science, medicine, psychology, and etc. However, scientific knowledge is growing in a very fast way. So let's take archive submission as an example. In the last month, which is May 2025, there are nearly 25,000 archive submissions made in that month. However, the knowledge of language model is static. So which makes that their scientific knowledge will quickly become outdated, severely hinders their reliability and helpfulness. So therefore, it is super important to do scientific knowledge update, to update language model with latest scientific knowledge, to keep them aligned with the latest discovery and keep them aligned with this evolving field. So then here comes the question. What should an ideal, reliable, and effective scientific knowledge update achieve? So prior work thinks that take the acquisition of new knowledge as the primary goal, where they mainly evaluate whether language model can effectively and correctly acquire new knowledge. However, in this project, we argue that the effective and reliable scientific knowledge update should do more than that. It should also preserve existing scientific knowledge, the parametric knowledge already encoded in the language model, and also project future knowledge to reason about future or yet undiscovered knowledge. Because we argue that past discoveries serve as the foundation for future advancement and remain valuable for researchers seeking historical context, validation, or reinterpretation of previous findings, which is different from other domains where people usually do knowledge editing to replace some previous finding with new finding. But here we want to preserve the prior knowledge while incorporating new knowledge. And in terms of projection, we think that it evaluates the utility of knowledge updates, enabling model to internalize new knowledge, moving beyond merely factual memorization to understand the underlying patterns or principles that govern such knowledge. And this capability can facilitate advanced reasoning, hypothesis generation, or the formulation of novel ideas, which are the key future usage of AI for science. So in that case, we introduced ScienceMeter, which is a novel framework for evaluating how language model update and reason over scientific knowledge. And ScienceMeter operationalized on the level of scientific claims, since which are atomic verifiable statements expressing findings about one aspect of a science entity or process, which can be verified against a single source. While prior work usually takes scientific knowledge as factoid information or structured entity tuples, we argue that scientific claims are more appropriate and meaningful units of knowledge in scientific context, since they can better capture the core insights and implications of research beyond isolated numerical values. So concurrently, what ScienceMeter evaluates is the preservation of existing scientific claims and their linkage to existing literature, and also the acquisition of new scientific claims from emerging research, but also the projection of future scientific claims. For example, when we update language model with a new paper introducing the effective identification of features of microglia, our framework evaluates the acquisition of this new knowledge as well as the preservation of existing knowledge about the fundamental of microglia learned from previous literature, and then the reliability and the ability of language model to effectively use its parametric knowledge to extrapolate future knowledge on microglia, such as its potential roles in the Alzheimer's disease. So then let's dive deeper into ScienceMeter framework. First of all, dataset construction. So we identified 10 rapidly evolving scientific domains, which are computer science, medicine, biology, material science, psychology, business, political science, environmental science, agriculture and food science, and education. Language models are increasingly integrated into the scientific research across these domains, so that it is important and crucial to access whether language model can continuously contribute to these domains through knowledge updates. And then for each domain, we retrieve 1,000 journal or conference paper published at least 3 months before the knowledge cutoff date of a specific model given using Semantic Scholar API. So this 3-month window accounts for the potential discrepancies between a model's online availability and its official publication date, ensuring a more accurate representation of knowledge. And then to obtain the more recent knowledge on the subjects related to this paper, we perform additional query to Semantic Scholar API, retrieving paper that cite the original paper and or published at least 3 months after the knowledge cutoff date. And then we also select a recent cutoff date, beyond which papers serve as the proxy of future knowledge. So in total, we construct 5,148 triples of knowledge, each representing the prior, new, and future version of scientific knowledge on the same topic. And then to get the scientific knowledge of each paper, we do synthetic generation of scientific claims. So for each paper, we generate 1 support claim, which we define as uniquely supporting claim, and 1 refute claim, which is a relevant but non-supporting scientific claim. Expert evaluation on those synthetic generated scientific claims shows that at least 80% of generated claims strictly follow our expectation, while over 95% broadly follow our expectation, validates the effectiveness of our claims.
Quick question. Are you getting these claims manually or do you use?
We synthetically generate, so use language model. And then
relevant claim, sorry, the refute claim. Is it just irrelevant or is it false?
It's relevant but not supported.
Oh, okay.
Yeah, so it's relevant to the paper but cannot be supported by the paper.
Oh, I see. So it's a true claim but just not supported.
Yes,
okay.
All right. So then we have a group of papers, and then we want to evaluate models' scientific knowledge on those papers we collected on the level of scientific claim. So to this end, we propose 2 tasks, which are climate judgment task and climate generation task. So for the climate judgment task, regarding in the terms of prior new knowledge, we frame this as a climate verification task, where given the title T of a prior or new paper and one of its associated claim, we ask the model to do a verification task on whether this claim can be verified by the paper. And in terms of future knowledge, since the model never saw those future paper yet, so it doesn't make sense to let it to verify against that paper. So we frame this as a claim classification task, that the model to do a classification on the claims, but it's solely on its internalized knowledge and its reasoning skills. And then the claim generation task is an open-ended generation task, which is a more harder setting than the claim judgment task, where for the prior and new knowledge, we gave them the title of the paper and let them to generate a supporting claim about this title. And then for the future knowledge, we gave them the subject of this future paper and let the model to generate a supporting claims. So. And after that, in terms of evaluation on those tasks, to better reflect the rigor of scientific domain, our evaluation methodology emphasizes both factual accuracy and model confidence. Since we argue that if the confidence is low, even if it is a factually accurate response, it is not reliable or useful this image just result from hallucination or random guesses. So by combining factual accuracy and model confidence, we categorize models' knowledge on each scientific claim as either correct, which is factually correct and confident, or incorrect, which is factually correct and incorrect and confident, or unknown, which has low model confidence, no matter its factual accuracy. So, and then using this categorization, we can now evaluate the effect of a knowledge update methods on models' prior, new, and future knowledge.
So a quick question as well. So when you say factually incorrect, so you said you talked about claims that were true and supported and true and not supported. But do you have now claims that are false?
Oh yeah. So by factual correct, we mean that the model's judgment on a claim is correct, which means that it's that support for a support claim.
Oh, I see. Okay, gotcha.
Yeah. Thanks for the question. All right. So now, given a set of papers and associated claim, along with models' knowledge on each claim, which can be either correct, incorrect, or unknown, we can systematically evaluate how a given knowledge update method impact the model's prior, new, or future knowledge. So specifically, let P prior, P new, and P future be sets of scientific documents in a particular science domain. And P new is introduced using a given scientific knowledge update method F, and let the G represent either claim judgment or generation task. And then, given a pre-trained language model LM and knowledge update method F, we can define science preservation and following. So here, the denominator is the group of claims from prior paper where the model's knowledge on that is correct before. However, after we update language model with the new papers using the update method F, the model's knowledge on those claims remain correct. And also for these group of claims, the claims made in their respective new documents need to be unknown to model before the claim the knowledge update. Otherwise, there is no knowledge introduced, so it's not a valid or real knowledge update. So, and then we also further define two arrow term, which we call distortion or loss. So the only difference here is this term. So the distortion is the proportion of those claims that become incorrect after knowledge updates, and the loss is the proportion of claims that become unknown after knowledge updates. So by definition, the sum of knowledge preservation, distortion, and loss is equal to 1. And then similarly, we define knowledge acquisition and the knowledge projection, where knowledge acquisition is the proportion of new claims that was unknown before that turns to correct after knowledge updates, where distortion is the proportion where it's unknown before but turns to incorrect, where the loss is the proportion that turns to unknown after knowledge updates. And similarly for the future knowledge, where we define knowledge projection as the proportion of the proportion of future claim that is unknown before that turns to correct. However, here we does not penalize distortion in projection because we think that some incorrect projection here might be correct in the future. We don't know about the future. So we did not penalize the distortion in projection. Well, the loss in projection is the percentage, it's a proportion where it is unknown before and stay unknown after the projection.
Sorry, and when you're saying correct and unknown, are you giving a claim to the language model, and are you giving a claim, or are you giving a claim in a paper?
It's also for the judgment task we give them for the prior new task we give them a claim and the title of paper, but for the future we just gave them the claim. And for the open generation task, we only give them to the title or the subject and let them to do open generation on the claim. So it's different settings.
You say you just give the title of the paper.
Yes. Yeah. So it has to use its parametric knowledge to.
Gotcha.
Well. So since
there's a question from Doug.
Oh yeah.
Yeah. So it looks like in all of these expressions, you're conditioning on the new claim being unknown.
Yes.
So like that. Okay. So that's like part of the experiment. Like you don't present a new claim that you haven't already verified is unknown to the model.
Yes, because though the new prior, new, and future paper are collected in a way that the model tends to be unknown to new and future paper and known to the prior paper, but we still do another round of validation here, so that we explicitly extrapolate, like elicit the parametric knowledge and calculate the projection, which is truly unknown, like to the model.
Got it. Thanks.
All right. So since I mentioned that some of the projection some of the incorrect projection might be correct in the future. So here, so the true magnitude of notch projection might is likely to be higher than our current estimation. So in summary, we define 8 terms, 3 core terms: notch preservation, notch acquisition, and notch projection, as well as 5 arrow terms. So by definition, the sum of preservation and distortion and loss is equal to 1, and the same holds for the notch acquisition. And also the other thing is that the distortion is more problematic than loss, which is because distortion means it is a factually incorrect response with high confidence, where loss, it means it's a low confidence response no matter of its factual accuracy. So generating a factually incorrect response with high confidence is more problematic than generating a response with low confidence. So that's why we think distortion is more problematic than loss. And we think that an optimal scientific notch update method should aim to collectively maximize both notch preservation, acquisition, and projection. All right, so then let's talk about experiment. So we experiment with 5 baselines across both training, inference, and jointly training and inference baselines. So specifically, we do continued pre-training, which auto-regressively train on the test documents, or standard instruction tuning, where we auto-regressively train on the pre and test document, and then following an SFT on the training QA. And following prior work, we also do pre-instruction tuning, where we do SFT before the continued pre-training. And also there's an inference baseline to account for some like retrieval augmented generation, or the add of like the results from search engine or other language model in the context window, where we present a text document at Inference-time. And we also do training plus inference methods, where we do standard instruction tuning plus inference to see if we use training and both training and inference methods can help with the performance.
So with inference, there's no training.
There's no training on the inference baselines. We just present the information like in the prompt test.
Yeah, so is that your baseline of what does an LLM know?
Oh, what?
Is that inference only task the baseline of what is the model, like what do the models already know?
Oh no, because in the inference baseline, we also present the new information and the context. So it's not just with the model. We also
Okay, so the update is, so for inference, the update is just put the new information in the context.
Yeah.
So these are like 5 different ways of updating the model.
Yeah.
Comparing.
Yes, exactly. So the continued pre-training, standard instruction tuning, and pre-instruction tuning are training baselines, and there's an inference baseline, and the last one is training plus inference baselines. And then following prior work on scientific domain, we only use the abstract of paper instead of the full paper, since they typically contain sufficient information and it's easy to fit within a model's context window. And we set the training duration of autoregressive training to 1 epoch and SFT for 4 epochs, and we train on the LoRa adapters.
Are you training on just a single document or multiple?
Oh, it's a group of documents.
How big's the group?
It's like it's different across different domains, but usually on the level of several hundreds.
Several hundreds. So for inference, do you put several hundred documents in the context?
No, it's just like for the inference we just put one.
How do you decide which one?
Oh, because it's like a triple. Because we have like all the groups of papers are grouped in a triple. So we have a older version of knowledge, new version of knowledge, and future version of knowledge. So in the inference baseline, whatever we are asking, we just group. We just put the respective new paper in the inference baselines. And then here's some results. So we experiment both tasks on both Llama 3.18b instruct and also OMO 230b instruct. Here, the Llama 3.18b is a representative of like a reasonable size, mid-size, and commonly used model, where the OMO 232b is a representative of frontier model due to the computation cost and the limited openness of like commercial models. And then we can see that from in a big picture that the no-notch update methods can simultaneously achieve all three objectives. They have various performance on different objectives, but we do lack of notch update method that can simultaneously achieve all three objectives. And also, in a big picture, we can see that the best performing notch update methods average across tasks and models preserve only 85.9% of existing knowledge, acquire 71.7% of new knowledge, and projecting 37.7% or more of future knowledge.
Can you just remind me what the colors mean here for the three different
Oh yeah, sorry.
objectives?
So here the pink means the knowledge preservation, and the blue is knowledge acquisition, and the yellow is knowledge projection. Sorry.
What would a random baseline get on the judgment task? This is just predicting supports or refutes, right? So would a random baseline get 50% on the judgment tasks?
No, because here we do not only consider factual accuracy but also model confidence. So the we don't know what a random baseline will get. Because even if the model has factually correct response, but if it has no confidence, we classify it as unknown instead of correct. So here it's not just factual correct or incorrect, but also model confidence.
Suppose the model made a random guess and said, I'm not confident at all. Wouldn't that still score like 50% or something?
Yeah, so you mean it makes an incorrect guess, but it
makes a random guess, yeah. Yeah, it makes half the time it's right and half the time it's wrong.
Yeah, but and also state like high confidence.
Well, it probably says I'm not confident. I suppose it says it doesn't have any confidence at all.
Well, actually make it harder, right? Let's say the model is like 100% confidence. It says support or reject. Like it's always confident.
Oh yeah, it's always confident. It's always
Half
correct.
the time right.
Yeah, then the baseline will be 50%.
So you're doing worse than random here then.
But it's only based on the assumption that the model is always confident. But how can you see that model is always confident? Like
Or it thinks we can pretend it thinks it is.
Oh yeah. So in that case, yeah, the baseline is like 50%.
What I want to know is do you have a bar or a chart or a plot for something that takes into account only the correctness, not the confidence?
Yeah.
Because this is entangling two things, right? Like this is entangling both the correctness of the claim and the strength of the model's belief in that claim for however you got that number out. Right, and so I'm kind of wondering about just that first part of just solely the correctness.
Yeah. So we did not include that part in the paper because we think that even if the model's generation is factually correct, but if it is inconfident, we mean, for example, if it has inconsistent answer using different prompts, or it shows inconfidence language in its generation, although it is a factually correct response, it is not reliable for user to use it, especially in the science domain. It's not super reliable because the model may be it might be something. So we take such response as unknown. So
okay. I mean, I would be curious to know still.
I see. Yeah, maybe you can also add that later.
Cool. Thanks. Ani?
Yeah, please.
How do you quantify confidence in all of these settings? Is it the same in all of those for all of those different baselines, or do you use different methods or something?
Oh yeah, so we use the same quantification for our baselines where we use 3 methods. So the first one is that we use consistency. So we frame the prompt 3 times and see if the other and the sample our response using different different prompt, and see if the model can convert to the same final binary answers. That's the first method. And the second method is that we following prior work, we append a prompt saying, do you need more information to answer these questions? So the indication of need for more information shows the lack of confidence in models generation. And the third method is the linguistic confidence, where we capture the linguistic incompetence, such as like unshown tone or unassertive language in the model generation. And then we judge the model confidence using the majority rule of these 3.
Okay.
All right.
Just one question. So for the third metric confidence, so that's for the generation task, right? Is it the language of the claim, generated claim, or is it the language surrounding the claim?
Oh yeah. So for the generation task, we did not use the last one.
Oh, okay. So it's for the judgment.
It's for the judgment task. So for the generation task, we mainly use the more information methods.
For judgment task, where is the is it like chain of thought style reasoning? Like where's the language? Isn't it just like binary classification with support?
So for the generation task, the response is just the scientific claim. So
For the one where you're using the language confidence, that's for the which task?
it's for the judgment.
Right, but for judgment task, isn't the output simply like the binary output support or reject? Like where's the language?
Oh yeah, it's not just the language. It's not just the binary answer, but also like the reasoning on those. So we do not like
I
ask
see.
for like just the binary answer, but also like reasons, like how do they come to this binary answer, and we can judge the confidence on those.
Do you explicitly prompt it? Do you say, how confident are you in this answer?
No, we use like consistency, linguistic check, and also the more information methods.
For the linguistic check, do you prompt the system to say, how confident are you, or do you just look for the word unsure?
Yeah, we look for the tone and the language use also.
When you say look, do you have keywords you're looking for? or
We use language model to judge
language models to judge?
the language, the use of words, language, and tone in their generation.
So converting all these qualitative measures to a number is challenging. Did you do like any sort of calibrations to see if
Mhm.
the number that you get out at the end is reasonable? From the
Yes,
beginning?
we do human validation on this method, this linguistic confidence methods. So it shows it's reasonable number. All right, then let's go on. All right. So, and then if we take a closer look at the results, we can see that among these 5 baselines, standard instruction tuning and inference baselines act as the best among these 5. And then due to then if we consider from the computational perspective, inference-based update method is significantly more cost efficient than the training, especially when updates are frequent. However, based on this results, we can see that the inference baselines only work for larger models, like more powerful models, whereas smaller models still require training to achieve compatible performance. We think that this discrepancy arises in part from the larger model's capacity to effectively filter out irrelevant or noisy contextual information during inference, where it was say like greater representational power or more robust internal attention mechanisms, which allows them to effectively like incorporate new knowledge at the inference time with minimum degradation of prior understanding. So also don't believe if we combine inference with training methods does not actually lead to sufficient performance improvement, which can be seen in the last column, since which suggests the diminishing return of training once the model has sufficient ability to leverage inference-based methods to incorporate new knowledge. So that's about training and inference. And then,
Just a quick question about the inference.
Mhm.
So you said you just put one paper in the prompt for
Mhm.
inference. So I'm just wondering if that's kind of giving a little bit of extra information, because you're providing just that relevant paper
Mhm.
for the inference task, whereas all the other knowledge updates, you're providing all 1,000 papers or whatever together.
Yes, so because I think we also do some like ablation on whether using like the same amount of like new documents as we use for training and the inference. So I think I didn't include that chart in this presentation, but we can see that the inference methods work for larger models where they have the capacity to like disentangle like irrelevant, like which is not related to this like subject before. But for the smaller model, it will be much harder for them. So.
Yeah, I mean, that's the question, whether if you put everything in the prompts, can the model ignore all the irrelevant stuff?
Yeah.
Or if you have a RAG system, can you actually retrieve the right documents?
Yeah, exactly. But if you put everything, all the like a ton of like papers in the inference time, it like the problem of long context might also be a problem. Because that may be like conflicting factors. Yeah. And then we also do an error analysis because we previously defined two types of error, which are distortion and loss. And we can see that in this climate generation task, which is the more harder setting than the climate judgment task, the amount of the distortion is on average 3 times higher than the loss in both preservation and the acquisition. Because we previously mentioned that the distortion is considered more severe than loss in both scenarios, so which makes this observation. So this observation actually suggests a significant challenge for knowledge update methods, as they may introduce error when they should remain cautious. So I think to address this, future development should like maybe incorporate some like, for example, upstream mechanisms to avoid update models representation if they lack confidence or is uncertain about the new knowledge, helping them to like preserve the accuracy and reduce the propagation of errors. And then we also further break down the performance by scientific domain and do a cross-domain analysis on the results. So here again, the first row is the knowledge acquisition, the second row is knowledge the first row is knowledge preservation, the second row is knowledge acquisition, and the blue row is the knowledge projection, and the x-axis is the 10 different scientific domains we identified before. So we can see that the performance actually varies significantly across different domains. While over 90% of knowledge in political science domain can be preserved, this number dropped to 72% in the context of material science. Similarly, while 48.6% of future knowledge in education domain can be projected, only 16.8% future knowledge can be projected in the material science domains. So, and we can when doing this cross-domain analysis, we also find that the performance on these 3 objectives is correlated. So if a particular domain do well in one setting, it also can do well in other settings. So that's why, and for example, such as like political science and education, well, like material science and environmental science, these 2 domains are like consistently poor. The performance in these domains are consistently poor. So why is that? We make 2 hypotheses. So we think that this might be relevant to the stability of domain knowledge. So which are like the which is like the how fast the knowledge in this domain change. For example, in the domain of political science, there are some like the knowledge is more stable. There are like long established series or principles that evolve slowly over time. So that which may make knowledge preservation, knowledge projection much easier. However, in the domains such as material science or like environmental science, any like experimental finding can like dramatically shape or change the paradigm of this domain knowledge. So which makes that the projection will be much harder. And also the other assumption we made is that it might be relevant to the availability of domain knowledge in pre-training corpus. So if the domain knowledge is widely used or in the pre-training corpus, the model might be more familiar with such domain knowledge, so the knowledge acquisition might be easier. So we make this 2 assumption and do experiments on that. So specifically, we use the average citation account of domain paper as a proxy of the domain volatility. So if the domain has a high average citation count, that makes the knowledge of domain evolve quickly. We use that as a proxy. And we use the pre-training occurrence of the domain-specific token as a proxy of the availability of domain knowledge in pre-training corpus. And we use infinigram to extract the availability of domain specific tokens in those pre-training corpus. And we can see that the two most pronounced correlation happens between the average citation count and preservation, where the Pearson correlation is minus 0.7, and also the correlation between projection and the average citation count, where the Pearson correlation is minus 7.36. So using this, we conclude that the preservation and projection exhibit strong dependence on domain volatility, whereas the availability of domain knowledge in the pre-training corpus demonstrate only marginal inference. So a highly dynamic domains with frequent updates may lead to more knowledge conflicts, making the preservation and projection particularly challenging. So that's our finding using of cross-domain analysis. And after that, rather than solely rely on off-the-shelf language model, research also use scientific language model, which are language models specifically trained or adapt to a particular science domain. So in this work, we also experiment with Honeybee, which is a llama-based model fine-tuned for material science. Since from the cross-domain analysis, we find that the performance on material science is significantly lower than other domains. So we wonder if we apply the notch update on scientific elements can help. So here's the chart showing the results across Llama 3.18b, OMO 27b, and Honeybee 7b. We can see that the performance on preservation, acquisition, and projection is on like scientific which is Honeybee, is not significantly higher than others off-the-shelf language model, showing that the updating scientific knowledge in terms of preservation, acquisition, projection is particularly challenging even for the scientific language model.
So just to make sure I understand. So with the so with knowledge, I see. So this is okay. So I see.
So it's a comparison between off-the-shelf language model and the scientific language model.
Can I ask you a clarifying
Yeah,
question?
definitely.
So, how do you know with the data that you're working with here, what the right amount of preservation, the right amount of acquisition, the right amount of projection should be, like when you're comparing across update methods?
Yeah, it's a good question. So here we think that the better the higher the number, the better the performance.
Across all of three.
Yeah, across all three. So because we think that ideally, like the most ideal like scenario is that we can preserve 100% of knowledge, like all the prior knowledge, and acquire 100% of new knowledge, and project like 100% of future, which is actually not ideal.
I see. So like if for example, like a new data point suggests that if a prior knowledge was false, and it was directly talking to a contradiction of some existing knowledge, shouldn't the prior knowledge not be preserved in that case when presented? Like new evidence?
Yeah. So I think one unique. So for now we did not like actually taking care of like what knowledge should be preserved, what knowledge should not be preserved. I think this is something really unique about scientific. Because in other domains, for example, some like factual domains, we do have like correct or wrong. Some knowledge are like outdated or misknowledge. We do want to replace it. But for the scientific domain, all the scientific advancement do make sense. So we do want to preserve them, even when we update them with new knowledge. So yeah, so that's what.
I mean, we have trivial counterexamples of like the best performing method on ImageNet is like AlexNet or whatever, right? Like, so there are certain classes of scientific claims that get invalidated over time, and like, you know, the best treatment for, right? Like many statements that are the best of and change, right? Like, so I don't, to your question, I still think the answer here is go towards one, because we've got so much room in acquisition and projection that like correction of the past, like error correction is not that big a concern yet.
I guess my understanding was that your claim verification or all these metrics are
Based on
relative
paper.
to a paper, right?
Yes, exactly.
So for that paper, it doesn't matter, right? And for a paper showed that image, like according to this paper, this is the best model.
So we
Or
should
to
not
another
change
paper, that's the
our
best
understanding of prior paper, even though.
But again, we have we have how well can a model follow a task?
Mhm.
And how much does its parametric knowledge, which you're updating, interfere with how well it follows a task? Again, we have two things going on, and it's like if you give like a smart person something, they might ask for clarification about like, okay, I know this is false. Right? Like if you give a smart person something that's been updated or they know to be false about the world and like a set of instructions, they might even ask for clarification about the instructions. Right?
But the questions are with respect to a paper, like does this paper support this claim?
Sure.
Or do you think that?
Right. And I
training
think that
support itself is under question.
I mean, I think the correct behavior there is not obvious because refusal from the model might be a correct answer. Right. So it depends on how you want to handle like that kind of inherent contradiction.
Yeah, I think it depends on how you frame your answer. If you're like asking specific understanding of a particular paper, that should be unchanged over time. But if you're asking like the most recent knowledge on like a particular term, that should be updated like, over time.
This 70% figure for llama.
Mhm.
So I'm naively taking this as for preservation.
Mhm.
So I'm naively reading that it's forgot 30% of its claims.
Of the claim made in prior
Yeah.
literature.
Feels like a lot for just doing some fine tuning on 100 papers.
Yeah, so that's why we think that it is important to study like knowledge update methods, because each time we update them, like a severe proportion of them are getting lost, or they're getting like distorted. Yeah, please.
I think in some domains, distortion might be much more frequent, even for the perfect model, right? As in, I'm saying even canonically, in psychology, for instance, which I think was listed as one of your domains, it's famously known that the half-life of knowledge is like very short, and all known models of psychology get overwritten pretty frequently, or half of them or whatever. So, and if you're averaging over all of these domains, essentially when you're reporting results, is it possible that a few domains might be just upping the canonical distortion numbers?
Yeah. It's your question that the amount of distortion loss will be will vary along across different domains. Well, in some domains there will
Yeah,
be
even for the perfect model, even for somebody, an oracle or something, some fraction of claims in prior work will be overturned by new papers or future papers or something, right?
Yes, yeah, exactly.
And this, I think, is larger for some domains than others. And I'm not convinced yet that this is not something we should be worried about while reading these results right now.
Yes, I think, yeah. So yes, I definitely agree that in some domains, like the distortion might be like more severe than loss. But in general, we can see from this chart that the distortion is like at least three times higher than the loss in like across different domains. So, but the actual like performance do varies across different domain, and the domain that is bad in acquisition will tend to be. The performance will also tend to be poor in like projection, the preservation. So.
Okay, I see.
Yeah.
Cool, thank you.
I had one clarification question. So I guess when you instruction tune, how does the instruction tuning example differ, I guess, from the test example on the judgment task? So like, do you actually instruction tune on pnew and train the model to, given this title and this claim, output supports or refutes, and then for testing acquisition at test time, you turn around and ask that same training question? Like, that must not be the case. So because you don't get, high enough accuracy. So what is the difference between the data you're presenting at instruction tuning time and the actual test question that tests for acquisition?
Yeah. So basically, we split because we have like 5,000-ish triples, where there's like prior paper, new paper, and future paper. We have like 5,000-ish triples, and then we split all this triple into training set and test sets. So during the training, we train them on the training sets of the new paper, and in the test time we test on the test sets. So it's just the training and the test set.
I see. So these are disjoint sets of examples. But I guess in what way then is there any way in which the test set documents have been presented to the model before? Like how could it have acquired this knowledge? And if you're doing continued pre-training, I guess I understand that. But in the instruction tuning setting, how does the paper PNU, how does that information enter the model?
Yeah. So if you can see in this slides, in the second row where I present the standard instruction tuning, where what we did is that we do continue pre-training on both training document and test document, and then we do SFT on the training QA. So here we present the.
Okay, got it. So it's still continued pre-training that you're relying on to load.
Yeah, but we mix with the SFT on the training QA.
Got it. Okay, thanks very much.
Yeah, thanks for the classification question. All right. Yeah, I think it leads to the conclusion of this talk, where in this project, we investigate scientific knowledge update of language model and propose an effective and reliable update methods to be able to not only acquire new knowledge, but also preserve prior knowledge and project future knowledge, which is crucial for the continued use of language model in evolving scientific fields. And we introduced ScienceMeter with rich data set and scientific papers along different domains with new tasks and evaluation of scientific knowledge and new metrics for evaluating knowledge update methods. And with experiments of 5 different baselines of frontier general purpose science and science-focused language model, we find that achieving these objectives remain an open research science challenge. So more effort should be put into further exploration on this direction. Yeah, I think that's pretty much what I want to share in this talk today. We have released the code, the data and the code on this GitHub repo, so feel free to scan. And we also present our paper in the archive. We're linked in this code, in this QR code. Yeah, thank you.
So right, folks asked a lot of questions during the talk, but we have some time for more questions if people have them.
Just one quick question. So I'm still thinking about this kind of 70% loss of prior knowledge from fine tuning. So it seems like a lot. And I thought there are new methods for continual pre-training like LoRa or whatever that aren't so kind of lossy. I guess my understanding was continual pre-training wasn't as destructive as you're showing. Do you think it's because you're looking at scientific documents, or is your task particularly hard? Or do you think you're using simple methods of continual pre-training? There are better ones.
Yeah, I think there are 2 main reasons. First is that it's scientific domains. So in a lot of in some scientific domains, such as material science and environmental science, the model does not have rich knowledge on that. And understanding those domain knowledge with some special symbols and notation will be extremely hard for language models. So I think that's one reason. And the other reason is that here we not only take account the factor accuracy, but also model confidence. So even if the model answer this like response factually correct, but if it lacks of confidence, we still like does not count that. So I think that's the other primary reason why this number is like kind of lower than like your like other studies.
A related question.
Yeah.
So for the acquisition, what are the numbers like? How like when you check for preservation acquisition, like how many claims are we checking? And for similarly for pre-training, the like continuous pre-training, how much are we trying to teach new knowledge? How does that compare to what it forgot?
Well, compared to what?
Like compared to what is like 30% of everything that it forgot. How does, and I think 20% or so is the acquisition rate, right?
Yes.
So how much new knowledge are you trying to, I think it's mentioned that earlier.
I think it's this like the overall.
Right, so like how much new knowledge are you trying to train? Like what does the training look like? Training on what?
Oh yeah, we train. I think per domain is like on average is like several hundreds of
700s of new facts.
per
New-
per
new
domain.
documents.
No
New
documents.
documents.
No documents. Yeah,
Papers.
Several hundred papers, okay.
per domain.
And then when you do the check, and the test, like these, the three tests, acquisition and preservation, so they are based on like you have a held out set of papers, like 100 papers or something.
Yeah,
equal
exactly.
number.
We have a trillion test sets, so it's destroying set of.
So like if I'm just thinking if the model, like these are just percentages, if the model had been trained on like 50,000 papers and it lost 30% of that knowledge, and all it gained was like 20% of several hundred papers, that's a pretty big loss overall,
Yeah.
right? It's just percentages are.
Oh yeah, and also you can take this percentage as like the absolute number, because like the number of like prior knowledge, new knowledge, and future knowledge are same, because like they're triples. So it's actually the percentage times the constant number for prior, new, and future.
But the prior knowledge itself is just, you're just testing on a small number, but the knowledge itself is like 50,000 paper or whatever it is.
Yeah.
Trained on, right?
Yeah, so because you said like they are percentage, but you can actually take them as like 85 papers or 71 papers, because like the in the test set they're saying like the prior, new, and future same.
It remembers 85% of the claims from 85% of the papers, previous papers.
Yes, exactly.
So if there were 100,000 papers, it has forgotten 15,000 papers. Like if this is a representative average.
Yeah, exactly. But
So that's a lot.
yeah. But suddenly I mean we also incorporate model confidence.
Right, that's even that.
So that's one thing which makes this numbers kind of lower.
It might be that it only loses confidence on the topical documents, loses knowledge on the topical documents. So for instance, we do continual pre-training on some new computer science documents, and it forgets a bunch of old ones, but maybe all the chemistry stuff is all in there still. Maybe.
How related are those tests? Like I guess the other papers for the
Triple.
the cripples, are they
Yeah.
related?
Those papers are just like papers that citing each other.
Are they
so-
citing each other?
Yeah. So it's not like 100% like significantly correlated with each other, but they should be
Yeah.
kind of correlated at least. Yeah.
So they're
That's better
related,
than-
so
Yeah. It's
it's not a random sample.
not an
Not
answer.
a-
Good, yeah, that makes me happier. Otherwise, yeah, you're losing like 15,000 papers per game.
no, okay.
200
Yeah,
papers.
we specifically
That's
curate a data set where all the knowledge are like super correlated, like some relevant knowledge. Because like prior research, I think when they update new knowledge, they test on the like natural question data set, which can be completely like
Exactly
irrelevant.
related. Yeah.
So those papers does not make sense to my understanding.
Do you know how many of these incorrect, like when your numbers go down, how many of those are because it went from correct to unknown, and how many
Yeah.
was just correct to
So the correct to unknown is the percentage of like loss in preservation or like and you can see this bar. So here the orange bar, which is loss, is the percentage that went from correct to unknown. So yeah. So but we think that actually loss is better than distortion. But because distortion is that you have like now you have a like false understanding of prior paper. But for the loss, you just forget about this paper. So not knowing something is better than like incorrectly knowing something. So that's why we think that actually distortion is more severe than loss. But yeah, we also have like a significant percentage of loss in one of these settings.
Any other questions? All right, then let's thank Yike again.
Yeah.
Thanks very much. All right, thanks everyone. See ya.
Okay.
Can you,
Do you-
stop the recording now?
Yes.
There's a technical similar to the usage which is well as pulling queries and often